Hello everyone, good morning. So the TuxSuite Ecosystem welcomes you. I am Sendil Kumaran and I was supposed to present this along with my colleague Alok. Unfortunately couldn't make it to the connect this time. So I'll go through this talk. So let's start with the usual question, what is TuxSuite? So TuxSuite is a set of easy to use tools which are on demand, and it also provides APIs in order to do different types of builds and tests. So the primary purpose of TuxSuite is to build Linux kernel, Android Open Embedded and Embed TLS, and also we can test with the help of TuxSuite all these builds that are being done. So what makes TuxSuite special is it is all container based, and it produces like reproducible builds, and also these builds are portable. Not only builds, the tests are also like reproducible, and it's portable. And we have a huge array of dynamic builder pool, which provides us with a robust system in order to do this builds and tests at scale. And what does that mean is like we don't have any idle servers. So this entire system is on demand, and it's very efficient in terms of cost in order to do the builds and tests. And each of these jobs are being run in isolation, so that is one of the important things, and we can scale to any level in order to do these builds at parallel. And TuxSuite is a combination of both open source tools and also like backend tools which are being used in order to do this builds and tests at scale. So what are the open source tools involved? We have tools like TuxMake, TuxBake, TuxRun, TuxLAVA, TuxTrigger, and also the TuxSuite CLI, which is the interface to interacting with different TuxSuite services which we have. So we'll get to that in a bit on what these tools do. So let's get into the capabilities of TuxSuite, what TuxSuite is capable of doing. So the first use case is builds. So with the help of TuxSuite, we can build Linux kernel for different kind of architecture at scale. So the underlying tool, the open source tool which is used in order to do this Linux kernel builds is TuxMake. And then we have the TuxBake, which is again an open source tool which helps in building open embedded builds. And with the help of TuxBake, we can also do AOSP, that is Android kernel builds, and also we can support building Android using the build scripts. Similarly, embedded TLS could be built using the build scripts which has been provided. And the second use case is testing with the help of TuxSuite. So we support two kinds of test devices. So one is the virtual devices, which includes QEMU and FEP, that is fixed virtual platforms, and also we can test using real hardware, that is on development boards and other real hardware. Even there are like some server hardware which has been supported by TuxSuite in order to do the test. So how this has been done, we have a Lava backend. With this Lava backend, we have different devices connected. So you can submit a test which is been built by TuxSuite, and then with these build artifacts, you can submit this test on a targeted device, whether it's virtual or a physical device, and then run your tests. So the open source tool behind the testing use case is called TuxRun, and that has been used in order to build at scale in our backend services. And we have a interesting concept called plan files, where plan files is a is a combination of different builds and tests. So you can define how you want to run these builds and tests, and how many builds and tests for different architectures you want to run. That could be defined in a plan file. So we'll get in a bit to how these plan files work. And then we have an interesting tool called TuxTrigger. So this is also an open source tool where TuxTrigger will help you to monitor Git trees and in order to do builds based upon a new release, based upon a commit, or based upon certain intervals in which you want to do builds. So Tux trigger will monitor based upon the configuration which you give. So it will monitor these Git trees and automatically trigger builds in our build systems in order to produce the different artifacts you require with the help of a plan file. And then the last is TuxSuite client. So TuxSuite CLI is the interface to each of these services which we are talking about. So each of these open source tools, that is TuxMake, TuxBake, TuxRun, and different things, has their own CLIs. So these are things which could be run on your local machine. If you want to build at scale and test at scale, as I said, we have different backend services which are being run on the cloud on demand, and these could be utilized with the help of the TuxSuite CLI, which becomes the interface in order to interact with these backend services which we provide as part of the TuxSuite ecosystem. So the first use case, let's see how a build works. I'm not going to show you a demo, but I have the screenshots in place because in short term doing a demo and breaking things in front of the audience is going to be very embarrassing. So I'll show you an overview of how the builds work and how we do builds. So the first thing is, so this is how we build with TuxSuite. So we have the TuxSuite CLI command, and we say build, and we pass certain parameters to it. So the first one is the Git repo, that is a Git tree with which we want to do the build, and the Git reference. So here we are doing a build with the master branch of this linux.git repository. That is the main line. And then we say which target architecture we want to build for. So we support a varied number of architectures as part of TuxSuite. And this is one of the interesting facts. So you can build at scale for different architectures and with different tool chains. So we do support different versions of tool chains. Specifically, the broader category is one is GCC, and also we also support Clang or the LLVM tool chain. And then we pass the configurations, that is here we want to do def config. You can pass different kconfigs modules, or if you want to build a tiny config, or if you want to do a all mode config, everything could be passed here. So once this command is fired, this will be built. So this kernel tree will be built for the branch that has been specified at our backend systems. So you can see first we are provisioning a machine in a backend system, and then we start running this build. It's basically a kernel build, and then once that is done, we have the build passed. So as I said, we have built this kernel tree with GCC 13 toolchain for the ARM64 architecture, and we are targeting on def config. So once this build is done, we have this URL which is being produced here. So what that URL contains is, it has these different parts as part of this page. So this is a build page which we have. So we have 4 different sections, that is parameters, results, timing, and the artifacts. So in parameters, as I said, so this shows what are the different parameters which we use for this build, and the results is whether the build passed or finished. And also we have how many errors or warnings has been produced as part of this build, and we can opt in order to use the cache or not to use a cache. So if we are using the default is to use cache in order to speed up these builds of the backend systems, we can also opt not to use the cache. So you can see we had 9852 cache hits, and then there were 60 misses. So as in when you start building again and again with this system, so the cache hits is going to increase. And then the timing, so how long it took for provisioning, running, and finish, and the overall duration of this. And the artifacts are being listed over here, and this is the main link, the storage, which has detailed artifacts and all relevant information which is related to the builds. So we also have the logs on how this build has been carried out. So how this artifacts looks like. So this is a build artifacts page. So as soon as I click on the storage, I have this. So the DTBs and this is the image, the kernel image that has been built, and other important information is available, the status.json and also the build log. So the build debug log has the timing at which each and every step has been carried out as part of this kernel build. So the next use case is test. So that is how we do build, and we have seen like how the artifacts get published. So the next one is test. As far as testing is concerned, we have a very similar interface where like we again use a TuxSuite CLI, and then we say test, and we mention on which device we want to test. So here I am going to test on QEMU ARM64, and then the kernel is nothing but the kernel which has been built, the image.gc, which I built in the previous step. And then I am asking the test use case to like do a LTP smoke test. So all these tests involve boot is a default test that will be run whether you mention it or not. So first it will boot, and then the requested test will be run. So the same kind of thing. So once we fire this, there will be a provisioning step and it starts running, and then we will have the results. And similarly, we have the URL, the artifacts URL, where you can see different artifacts as listed in the builds page. So I am not showing the artifacts page for tests, which is very similar to the builds page. So if you see here, in this we have booted QEMU ARM64 using the kernel which has been produced by the previous step, and then internally we use a QEMU system AX64 device, which is a virtual device on which we build. So similarly, we also can have real hardware if we have a Lava instance that is being backed up. So you can say like test it on a Juno or test it on a DB845C based upon the kernel which you are like which I've built. And then so I've asked it to run LTP smoke test, and similarly like the artifacts get stored here. Next thing is the plan. As I said, like plan is a concise description of what you want to do and how many builds and tests you want to do. So everything could be combined within plan is kind of a config file where you instruct, so these many number of builds I want to do for these different architectures, and after these builds are done, like automatically like trigger tests on these devices. So that is how a plan file works. In this case, if you see, as I said, like plans is a combination of builds and tests. So builds can trigger multiple tests. Once a build completes, the artifacts are generated. The artifacts could be pulled into tests in order to be tested in different device types. So this how a plan file looks like. If you see there is a version, you define the name of the plan and you say what this plan does, and then there are different jobs. So here majorly we are doing two things. One is we are building for the x86 architecture, and the second thing is for the ARM64 architecture. So the build is nothing but we are doing two builds. So with GCC 12 and also GCC 13. For the x86-64 architecture, we do a def config build, and once this build is done, what we do is we want to test these artifacts on QEMU x86-64 device. So I'm asking it to do LTP smoke and LTP commands test. So this is what is explained here. And similarly, for the ARM64 use case, I'm doing a build using GCC 13, a def config build, and again I asked to do a test on LTP smoke and LTP commands. So once this is fired, it will do the builds, the artifacts will be taken, and automatically a test will be triggered on these virtual devices, that is QEMU x86-64 and QEMU ARM64 device types. So once the plan is complete, you will have a plan page similar to the build page. So if you see, there is parameters, there is results, and also how many builds has been done. So in a previous step in our plan file, we defined like asked to do 3 builds, that is 2 for x86-64 and 1 for ARM64 with GCC 12 and GCC 13. So you can see that builds has been passed. If you click on each of these links, the artifacts page which I showed for the builds, it will appear. So similarly, like test, if you can see that for all the cases, like LTP smoke passed and then LTP commands test failed. So you can add any number of tests with this combination. So this has been used heavily by projects like LKFT in order to like do different testing and produce build artifacts on a day-to-day basis, and also for RC reviews. So this is an overview of how TuxSuite works and what are the different components and capabilities of TuxSuite at a high level. So there are like two important things which I want to talk about in today's talk, about like two features which we've been working on for the past year, and it's been something which has been stabilized now, and I want to like introduce that to the audience. So the first one is the kernel.org toolchain support. As I said, we can build for different kind of tool chains as part of TuxSuite. So kernel.org provides these tool chains, specifically the GCC tool chains and also LLVM tool chains, which has been published on that URL, that is mirror.ch kernel.org cross tools. So here we have these tool chain binaries that is being published by kernel.org. So these kernel.org toolchains are named as korg-star in TuxSuite terms. So why these toolchains? Because these toolchains are optimized for kernel builds, and it's been published by maintainers in kernel.org. So this this very much focused only for kernel builds. Unlike the other generic toolchains such as GCC 13 or 14, which we find in the Debian or Ubuntu operating systems, this is specifically built for kernel compilations. So we did enable korg Clang in May 2024, and as a follow-up, like last year, towards end of last year, we did add support for korg GCC toolchains. So korg GCC was a long time ask from the kernel community for almost like 3+ years, and it's a reality now. So as I said, like it's a different approach from using the Debian's stock tool chains, that is GCC or Clang. These tool chains are coming from kernel.org, and these are optimized. So the way in which we have adopted this korg GCC support in TuxSuite is, it is very well gels with the kernel engineer's workflow. So how it has been done? So we select x86 or ARM64 based upon the toolchain requested, and we have a TuxMake toolchain cache in which we download all these toolchains and cache it in the user's machine. This is specific to TuxMake, and also we verify the signature based upon the private key of the publisher. Predominantly, that is Arne Bergman from Linaro, who is like maintaining these toolchains in the kernel community. And then we extract it to build directory, and then we set up the cross tool prefix, and then once that is there, we load these toolchain binary in a container, a generic container, and then start running the builds, like how TuxMake used to run for other builds. So this is overall like view of how it has been done. So previously, like this korg base, right, is a Debian base which we have. So each of these toolchains, say for example, if it is like GCC 13, we rely on Debian, say Bookworm, in order to like have that stock toolchain coming from the Debian repositories. Now what we have is a single container where we have the base tools that are required in order to like do the compilation, and then the toolchain itself, that is the toolchain binary of GCC toolchain, comes from the kernel.org repositories, and then that has been pulled into the runtime, and then there is a cache, and we do the compilation based upon which toolchain has been requested. So there are some important things to note. So there is only one single container which we publish instead of the different combinations of containers which we used to publish for Debian based toolchains in the previous way of working. So this is a very big optimization in terms of how TuxMake itself works. And then we were able to add support for some old toolchains also. That is, we support GCC versions from 18 to 14 as of now. And with this introduction, we also have introduced support for 12 new architectures which were not being supported previously as part of TuxMake. And TuxMake also gives a way in order to download all the tool chains at one go within a separate cache. So the known issues are like it doesn't support null runtime. It's a internal feature of how TuxMake works. We can choose whether to run TuxMake in Docker or Podman or different things, different runtimes. So null runtime is not supported as part of korg-gcc toolchain in TuxMake. And then we don't have support for GCC versions 7 and older. That is, we don't support GCC 4, 5 or 6. So only we have support from 8 to 14, and there is a purpose for that. Probably we may add if we could figure out some of the legacy things which GCC wants in modern operating systems which are available today. So the next thing, I will not take much time in order to go through this. We are already running out of time, I guess. So the other important thing is TuxLAVA, which we have been working on lately. So what is TuxLAVA? So most of you in this room, I think you're aware of the system called Linero Automated Validation Architecture, which is nothing but Lava. It's a system which helps in order to do test validation for different kind of kernels on physical hardware. So in order to generate jobs or the job definition for Lava, we have this project called TuxLAVA, which is part of the TuxSuite ecosystem. And TuxSuite uses TuxLAVA internally in order to generate these Lava jobs to be submitted to different Lava instances across, whenever it has been requested. So what TuxLAVA is, it is a Python, both a Python library, it could be used as a Python library and also a command line tool. And we support a standard list of devices. So we support devices like AVH, Fastboot, FEP, NFS, QEMU, and SSH. All devices. Specifically, there are more devices based on Fastboot and also NFS that has been supported by TuxLAVA. And it also replaces the majority of code base in TuxRun, which is the purpose why TuxLAVA was born, in order to separate a lot of code, written in code, which we want to maintain independently. And what is the future work for TuxLAVA? We want to do health check standardization as part of TuxLAVA. So that is something which is underway, so that if any Lava instance exists, if they want to have health check for different device types they support, they can use TuxLAVA in order to generate these health checks, which are getting standardized. So this overview of how TuxLAVA could be used as a Python library. So you can just use the job class in order to define what is the device kernel and also the different parameters you want, and then you can render this job, which will produce a full-fledged Lava job file, which could be submitted to different Lava instances. Similarly, it could be used in the command line. It is been available in the PyPy repositories where from where you can install it, and work is underway in order to provide TuxLAVA as a Debian and RPM package, which will be soon available. And as I said, TuxLAVA is a completely open source project, and it's in the initial stages, and we welcome contributions to this project. So if you want to use TuxSuite firsthand, and you want to account, you can contact TuxSuite at linero.org. We'll be able to help you in providing tokens in order to access our backend systems in order to do builds and tests. We have a separate community membership where we provide certain number of builds and tests on a free basis on a for the users who are requesting it. And also we have commercial usage of TuxSuite, where if your company who is looking for doing builds and tests at scale using TuxSuite, we can talk to you in order to do that. So thank you. Any questions? Okay, I assume there is no questions. Thanks for listening. Thank you.